Okay, the main aim of this video is to now go through the aromaticity. Okay, we want to determine whether the compounds we are going to be going through right now, the examples, about 5 of them, we want to see if they are aromatic or they are not. Okay, frankly speaking, we group them into 3, like aromatic, anti-aromatic, and non-aromatic. But you don't need to know that. Okay, you don't need to know. What I just want you to know is it aromatic or it fails to be aromatic? Because we know that when it fails, we can group it into alicyclic, right? So now we want to see what it is that we use to know if something is aromatic. So for aromaticity, right? Aromaticity, we use the following criteria, the following 3 things. Okay, I'm going to keep them as simple as possible. First thing is that your compound must be cyclic. Okay, your compound must be cyclic. It must be cyclic. Okay, we must have a complete cycle with no breaks, right? We don't want it to be branched, or we don't want it to be unbranched, whatever. We want it to be cyclic. Number 2 is that your compound must be conjugated at all points. Okay, conjugated at all points, or should I say, it must be all points in the ring. Okay, it must be conjugated at all points in the ring, or it must be planar. Let's say and planar. Okay, it must be planar. Then number 3, it must follow Haeckel's rule. Okay, it must follow Haeckel's rule, where it says the number of pi electrons should be equal to 4n plus 2. So your number of pi electrons should be equal to 4n plus 2. You say to me, what is n? Well, n is representing whole numbers from 0 going up, or let's say integers from 0 going up, right? From 0 going up. Integer means just whole numbers, but including 0 also. So from 0 going up. So in other words, what is the numbers that we are agreeing? If n is 0, then it will be 4 times 0 is 0 plus 2, it will be 2. So the possible numbers should be 2 pi electrons, the number of electrons in pi. Or if n is 1, it will be, now let's say n is 1, it will be now 4 times 1, then plus 2. And what do you get? 6. So it will be 6 pi electrons, right? Or if n is 3, remember n is just taking whole numbers. It is just taking numbers. If n is 3, it will be 4 by 3, which makes it 12 plus 2. Let's start with n is 2, sorry. When n is 2, it will be 4 by 2, it's 8 plus 2, 10. So it will be 10 pi electrons. If you see something, we are just adding 4. So the next one will be 14 pi electrons. And the next one will be 18 pi electrons. So these are the only possible numbers. So when you count the number of pi electrons, they must be either 2 or 6 or 10 or 14. If they get another number which is not one of these, okay, then it doesn't qualify to be aromatic. What do we mean by the carbon must be conjugated at all points in the ring? We are just saying all the carbons must be sp2 hybridized. We mustn't have an sp3 hybridized carbon. If we don't have this conjugation, then we must have a lone pair. We must have a lone pair in p orbital. So I'm going to do examples with you, then this would make sense. So either we must have, look at this. Let me explain to you or more. You can go and check the video on hybridization if you want to understand the difference between sp3, sp2, and sp hybridization. Basically, if your carbon can form a maximum of 4 bonds, right? If carbon forms 4 single bonds that are separate, then it is going to need to have sp3 hybrid orbitals. Okay? And these would be 4 of them. If carbon is making 4 different bonds, single bonds. But if carbon has a double bond and then some other 2 bonds, then it's going to be sp2 hybridized. Okay? 1s and 2p's, right? It only needs 3 orbitals. If carbon has a triple bond, then another single bond somewhere, then it will be sp hybridized. So what we don't want is we don't want a carbon that has only single bonds. If you ever find that type of a carbon in your structure, then that thing you are dealing with is not aromatic. If it's aromatic, it must have a double bond somewhere. So basically we're saying the carbon should have a double bond somewhere. Okay? All right. So one, the carbon must be sp2 hybridized. It must have a double bond somewhere. Another thing, if it's not a carbon, then whatever you're looking at should have a lone pair that is in the p orbital. We'll see how to see that. And then the other one is your compound must be cyclic. So let's look at the examples and we choose together. Example 1. Okay, here's your example number 1. Let's say you have something like this. Forgive me, I am that much of a bad artist. Okay, your example 1, let's say you have something like this, and then it goes down, and then it goes down. Okay, let me say it goes down, then here it should go down. I'm not drawing it properly. Goes down, then here it should go down, and then it goes down, here it goes down, then these two lines join. Okay, something like this, right? Then we have, say I'm going to put a double bond here, and let's say I put another one here, then let's say I put another one here. Then I say to you, is this aromatic or not? This is your example 1. Is it aromatic or not? So let's go through the 3 criteria. 1, is it cyclic? Yes, it's cyclic. Okay, in here I'm doing the bond line formula. You can go and check again the video on bond line formula. We know that at every corner, whenever you see a corner, there's going to be a carbon unless they put something else. So we can see that there are carbons at every corner, right? So we're going to say, is it cyclic? Yes, it's cyclic. It goes around. Now, second one, do we have flat and conjugated? Is it flat and conjugated? Okay, it means do we have sp2 hybridizations? Okay, basically why do we need that? Because we need the other p orbital to form pi bonds. Every location should have a p orbital that is there, and we know that when a p orbital is there, right, when you have your lobe structure, because pi bonds are made by p orbitals only, you know that. So if you have your p orbital being there, and let's say here we have another p orbital, let's put it, I'm such a bad artist, right? We know that there's going to be overlap here, and that's a pi bond. So we need every corner to have a p orbital so that we can have these pi bonds, eh? We want to have these pi bonds, and we want to have overlapping, sideway overlapping. That is pi bonds. So we need the p orbital. So we need sp2 hybridization. sp2 hybridization will leave one p orbital being free, and that p orbital is the one that is used in this bond creation. So, wow. Is it flat and conjugated? We look at every corner and see if the carbon has a double bond somewhere. If we look at this carbon that I'm circling here, it has a double bond on its right and then a single bond there. Okay, which is not really the case, but I'm just, okay, if I put here, what do we have? This carbon that I'm circling here, it has a double bond. Yes, it does, and a single. Okay, so it's fine. What about this one that I'm now circling here? Well, it has a double bond on it, behind it, and then a single, so it's fine. Then what about this one? Let me circle it in yellow. What about this one that I'm now circling here in yellow? Look at it. On the right, it has a single. On the left, it has a single. On the right, it has a single. So this is definitely an sp3 hybridized carbon, which is our enemy, an sp3, because it's just going to make 2 more bonds with hydrogens, and there we have our sp3 hybridization because it has 4 bonds, and that's an enemy that should never be there in aromatic. So that means this thing has failed on conjugation, so therefore it is not aromatic. Okay, we can already say it's not aromatic. We don't have to test the 3rd criteria. If it just fails 1, it's good enough for it to fail, right? Okay, let's go to example number 2. We are going to say example 2. let's put something nice and let's enjoy. I hope you're improving, getting better. Now we are going to say, number 2, we just make something that is a bit not too complicated. Okay, just a bit nice, like that, like that. Now let's go through the things. We have 3 criteria only, right? The first one checks, is it cyclic or not, right? So the first one, is it cyclic or not? On cyclic, yes, it is cyclic. There we go, because it's all the carbons are connected, interconnected at the 4 corners. Then the next thing, is it planar and conjugated? Do we have conjugation? Okay, is it conjugated and planar? Well, we had a free thing. Is it conjugated at planar? What would you say? We say, do we have a carbon or a free carbon that doesn't have a double bond? If we look at this one in the corner, it has a double bond here. If you look at this one in the corner, it has a double bond here. Okay, if we look at this one in the corner, it does have a double bond. If we look at this one in the corner, the last one, it does have a double bond. So done. Okay, they're conjugated and planar. They are all the carbons have a double bond. Now the last thing you're going to check is, does it meet Haeckel's rule? Okay, Haeckel's rule, right? In Haeckel's rule, how do you do it? How do you find? Well, every double bond has 2 pi electrons. Okay, every double bond has 2 pi. Now Haeckel's rule says we need the total number of pi electrons to be 2 or 4, 2 or 6 or 10. Right? It keeps going. So if we see here, we have increased, right? Why are we increasing the we have Haeckel's, right? Why are we now counting? Let's say we are counting to please Haeckel's number. Haeckel says we need 4n plus 2. How many number of we have here? We have 2 pi electrons there. Then here we have 2 of pi electrons. So definitely on Haeckel's we are going to say we have 4 pi electrons. And this is wrong. So it's not aromatic. It is not aromatic. Okay, that's it. Now we are going to go to example 3. Let's see example 3, what it's going to be like. Well, this one we are going to put in oxygen with 2 lone pairs. Then we make it do that, then do that, and then when it gets here, it comes back in, and then we connect the points like that. Then we're going to put a double bond here and a double bond there. Now let's go and see if this is we go through this example, and all we want to find out is this thing aromatic or not? This is the example 3. So first of all, we say, is it cyclic? Yes, it's cyclic. Don't be confused by this oxygen. It is cyclic. Okay. Then now we say, do you have conjugation? Okay, conjugated base. So here let's say conjugated and planar rather. We saw that it was cyclic. Now let's see conjugation. Conjugation, we said we are going to look at all the carbon atoms in every corner. This one has a double bond here, so it's fine. This one has a double bond there, so it's fine. This one has a double bond where we are coming from, and a single bond. Then this one also has a double bond from where we are coming from to where we are going. Now, all right, we are fine. All the carbons are G. Now, but what are we doing? Let's see. All the carbons are good. What are we doing? We are stuck on the oxygen. We want to know, is the oxygen having a lone pair? We see that it has lone pairs. Lone pairs are these 2 electrons. There will be 2 of them that did not participate. That's why they're called lone pairs. Pairs is to say they move together. They're in 2s and they did not attend, right? Okay. So now what are we saying? Conjugated and planar, we'll be saying, how do you see if something with lone pairs is going to qualify? You look, either it should be in a double bond like this oxygen, or the nitrogen should be in a double bond itself, or it should be one step away from it. So if it is one step away from it, then you are going to count, okay, then you're going to count your let me not move the arrow like that. Your lone pairs to go into a p orbital. And once they do that, because all we need is a p orbital so that they overlap sideways. Okay? Okay, so that they overlap sideways. So here, that's what we are saying. We have an electron in the p orbital. Once we have it, that was the only missing position that was left. So therefore, it is definitely conjugated and planar. Now, the last thing we are going to look at is, does it meet Haeckel's rule? Because it has met the other 2. Does it meet Haeckel's rule? Well, if we for it to meet Haeckel's rule, let's count the number of pi electrons. This polarized guy gave away 2. Okay, this Haeckel's the what do we say? We are saying the oxygen, this oxygen that has lone pairs, will give 2 of its lone pairs into a p orbital, because a p orbital can take 2, right? So it's going to be 2. That's the only place where you find 2 in one place. So you're going to have 2 pi electrons, okay, electrons. Then plus, what about at every other double bond? At every other double bond, we're going to have again 2 at every double bond. Okay, so we are going to say here we have 2, so it's going to be 2 pi my, right? So it's going to be 2 pi. We have 2 more, right? So yes, we put it down. So it'll be 2 pi electrons. Then plus, here we have another 2 there. So it'll be plus again 2 pi electrons, right? And what do we get? 6 pi electrons. And what does Haeckel's number want? Either 2 or 6 or 10. So definitely it qualifies. And therefore, this is aromatic. So you see how we check if it's aromatic? Yes, the carbons definitely must have a double bond. If there is no double bond on all carbons, then we have a problem. Okay, that's the simplest way to say it. Now we look at the last 2. We are almost done. Let's look at the last 2. Right, number 3, we would have something like this. It is going to come like that, go down like that, and then go down where we will have our nitrogen, and this nitrogen will give him lone pairs, right? Which he does. So here we are going to have something like this and like this, and another one here. Then, okay, now is this aromatic or not, right? Is this aromatic or not? First, we check if it is cyclic. That means it goes in a cycle. Yes, it is. Okay, don't be confused by this word. It is cyclic. Then, now the next thing is to check for what? After seeing that this is cyclic, then you're going to check at every corner, right? Don't ever forget that after you find it is cyclic, then now you're going to check at every corner. Like if I put in white, I'm going to check at this corner for carbon here, and this corner there, and this corner there, and this corner there, and there. Then I'll check my nitrogen if it is a lone pair in the P. So, right? Then I'll check my nitrogen if it's going to have a lone pair, okay, in this 3. Once I can get it, then I'll be done. So here we can write conjugation, okay, conjugation or conjugated, and if it is it planar. So now what do we see that? We see that this carbon has a double bond here, right? And this carbon has a double bond there again, okay? Then we have this carbon, it has a double bond there, and we have this carbon, it has another double bond there again, okay? Now we have this carbon there doing that, which is good. Now the last thing, right, for this nitrogen, since you are seeing it is already involved in a double bond, the only way it could be involved in a double bond is if it had those p orbitals. So this is okay. So now what we are going to say is, okay, this nitrogen is fine because it's in a double bond, right? So it's in a double bond. So conjugation is good. We looked at everything. Then the last thing, okay, the last thing now is going to be Haeckel's rule, okay? Now, what am I going to do here? Well, all you're going to do is count the number of pi electrons, right? Wherever there's a double bond, how many do we have? 2 pi electrons. Then here, how many bonds do we have again? 2 pi. Then here, how many bonds do we have again? 2 pi, right? Is it true? So that means this is going to qualify because it has 6 pi electrons. Done. Okay, that's it. Now we look at the last one, the very last question, and it's going to say, so you see how to see it? Yes, that's how you see it. Number 3, you can repeat. Number 4, I mean, is it number 4 or number 5? Example 1, 2, 3, 4. This is example 4. And then now we are on example 5. Okay, now what is it? You're going to have example 5 is going to have sulfur, 2 lone pairs, top and bottom. Go down, 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 like that. Then come back with 2. Nice, same thing. All right, so now it's like going to be like this, then like that. Then what are we going to do? What are we going to do now? We are going to check, is it cyclic? Yes, it's cyclic. The only reason we put this S and O is they're part of the cycle, so it's heterocyclic. Then another thing, what is it? They said it is flat conjugated. Okay, so here we want to check if it's, oh my, sorry, almost done. We want to check for if it is indeed, okay, conjugation. Okay, conjugation. Now we are only going to check, let's see if it's going to be, okay, conjugation. Let's see if we are going to have that planar at every point. We need a p orbital at every point. Okay, so we need, if it's a carbon, to have a double bond somewhere. And then here it's because now how do we know if it's going to have a p orbital, this S? Okay, because sometimes it doesn't. If it doesn't, then definitely you know that you can't say it's aromatic. But what you do is you know that if one of these two lone pairs is going to go into a p orbital, and that's for stability and resonance. Okay, that's for another day. So that means here we have 2 pi electrons because they go together. And then this double bond, you have another 2 pi electrons. And then here is oxygen you bury. It has 2, so definitely 1 will go, and that will be 2 pi electrons. Then here you are going to donate again 2 pi electrons, right? So it's going to be 2, 4, 6, 8. It's going to be 8 pi. Okay, it's going to be 8 pi electrons, right? 8 pi electrons, 8 pi electrons. Now, is that a number we want? No. What do we want? 2, 6, 10. So it doesn't qualify, therefore it's not aromatic. Using this, now we can be able to group everything. Okay, bye for now. See you in the next video.